Hello and welcome to the seventh video in our lecture on access control policies and mechanisms. Notice that in this video we are focusing a lot more on the policy level than the mechanism level, and this is going to be even more true in this video because we're going to be talking about multi-level security models. These models describe some properties that must hold, and therefore they are really focusing on explaining what needs to be done, not how to implement the system to satisfy those properties. So these multi-level security models that we're discussing in this video, they're designed to express the requirements of the system, the security requirements, not their implementation. So they're definitely positioned at the policy level, and also, as we're going to talk about in a minute, at the assurance level. So what these models are doing is they are describing the properties that the system should have. They are not prescribing how to implement the system to meet those requirements. So they're really a high-level description, not so much an algorithmic description of any kind of technical system. Again, they're describing system properties that if those properties can be met, then it's possible to prove that the system is secure. And this is the assurance part. If you're able to prove formally that the implemented system meets the properties that are set out in the model, then you have assurance of the security of the system. So again, this assurances are really theoretical, much more than practical. Again, these are formal systems that are pretty abstract. In fact, there are many multi-level security models based on the different levels of abstraction and the amount of detail that they cover. Here, we're only going to cover the most famous multi-level security model. It's also the simplest. That's why it's popular, and that's why we can discuss it briefly. There are other models that exist that are more realistic, but they're also much more complex. They are much more difficult to explain. They are much harder to verify formally, and they are, most importantly, much more difficult to enforce. So it's not clear how practical they are. So the model in question, that is the focus of this video, is the so-called Bell-LaPadula model, named after the two people who developed it in the 1970s, and we're going to call it the BLP model for short. So this model establishes two formal properties that are important for access control. The first property is called the simple security property, sometimes called the SS property for short. So remember that we're dealing with subjects or users or processes and objects, that is, resources or documents. And here we're going to assume that a subject is able to read a particular object, a particular document. So the SS property is that if this is the case, then equivalently, it must be the case that the security level of the object is less than or equal to the security level of the subject. So remember that L stands for label. We can also call it, interpret it as the level. And remember that the security label of an object is called its classification, whereas the security level of a subject is called its clearance, his or her clearance. So what the SS property says that if S is able to read O, that it must be the case that the clearance of the subject must be at least as big or equal to the classification of the object. So that kind of makes sense. What it's saying is that if S is able to read document O, then S must have a security clearance that's at least as high or potentially higher than the classification of the object. So, in other words, a person with a security clearance of, say, secret can read documents whose classification is either secret or lower. So, a secret clearance person can read all the documents that are at the secret level, or the confidential level, or the public level. But they are not, or unclassified. But they are not allowed to read documents at the top secret level. So another way to summarize this simple security property is to say no read up. Again, a person, a subject at a particular level is not able to read a document or access a resource at a level that is higher than their clearance. And that seems pretty obvious, so the name simple security property makes sense. So another way to say it is the object can always read down but cannot read up. The second property is a little bit harder to grasp. It's called the star property for some reason. And again, we assume that we have a subject and an object. And instead of looking at the read access right, we're going to focus in this property on the write access right. And this property requires that if a subject S is able to write or modify a document or resource O, then it must be the case, and this is an equivalence, that the security clearance of the subject is less than or equal to the classification of the object. So what that means is that for a subject at a particular clearance to be modifying a document, they can only do so if the document has a clearance that's either, or classification that's either at the same level or higher. So what that means is that everything that a person can write will only be accessible to people with the same classification or the same clearance than them or higher than them. So a person at the level of, say, confidential is going to be able to write documents that only people with a classification, with a clearance of confidential or secret or top secret are going to be able to read. So a person, again, at the confidential clearance level cannot write a document that will be classified lower than their clearance, say unclassified. So there will be no write down. Or another way to say it, that a person can only write up. So in fact, another name of the BLP model, an informal name, is called the read down, write up model. So it's important to realize that these two properties are really focusing on the confidentiality security goal that we talked about uh, from the beginning of the course. So in the context of these mandatory access control policies, the Bell-LaPadula model is really focusing on one goal, which is the confidentiality one. And so what it's saying is basically no subject can have access, either a read access or write access to any resource in the system unless those two properties are satisfied. So this simple property, I think, is more intuitive and kind of easy to understand, that you're not allowed to read documents that are above your security clearance. But this property is a little bit less obvious, the star property, the no write down. So on the next slide, I just grabbed a picture that is an attempt at explaining this property, the star property. So let's assume that you have two levels of classification for documents. You have a high level document and a low level document. And let's assume that you have a subject that also has a high level clearance. So really, this subject is able to clearly read document at this level because this is the same classification level as their clearance level. But to protect against a potentially malicious subject with such a high level clearance, the star property states that whatever document this person can write or modify cannot have a classification level down here, which would be lower than their own clearance. So I think the reason this makes sense is because if this person was able to write documents that have a lower classification than their own clearance, then they would be able to access highly classified documents and then basically copy them down to a lower level of classification, which would then kind of leak this classified document down to the lower levels, people with a lower clearance than themselves. So that's kind of the justification for the star property. So to wrap up this discussion of the BLP model, we should mention some high-level characteristics of it. First of all, it's pretty simple in the sense that it only has those two properties. So that's kind of a downside because it's not very refined. However, the advantage of its simplicity is that because of that, it's one of the few security models that allows people who use it to actually prove definite security properties for a system. Now, because it is so simple and so popular, uh, it has generated and motivated the extensions to it. So there are many other security models that have been defined after it. And the advantage of those models is that they are much more complex and much more realistic. But on the other hand, for that reason, they are much harder to analyze, and it makes it much harder with them to actually prove definite results about the security of the system. So remember here, we're really talking about high level models. We're talking about policy level and assurance level. Once you get to the technical details of implementing the system, it gets pretty tricky. The more complex these properties, the trickier it gets to make sure that the implementation actually satisfies those properties. So another main feature of the BLP model, as I've already discussed, is that it really focuses on the security goal of confidentiality. So what it's trying to enforce is that there is no unauthorized reading of information. It's trying to limit the chances of disclosures. But what it's not focusing on is the other security goal, the second one in the CIA triad of integrity, the unauthorized writing of modification of resources or documents. So there are many other models that have been developed to deal with integrity. One of them is called Biber's model, named after the person who developed it. Again, we're not going to talk about this model, but you should know there are many, many other models developed after the BLP model. Another main characteristics of the BLP model is that the second property, the star property, is actually very hard to enforce. Think about situations, which is basically everywhere in the real world, where we have shared resources, and that's typically the case for big organizations. And then we have covered channels. So covered channels are basically channels that are not supposed to exist, but still are very hard to prevent. So, for example, let's assume a system was implemented using the security features of an operating system. So we would have an operating system with multiple levels of security, like it's been done with different rings, for example, with the kernel at the center and different rings of security around that. Then, the operating system is actually implementing very specific mechanisms, but the BLP model assumes that the only way that subjects can communicate with other subjects is through the operating system. But of course, that is not the case in the real world. So the star property only works and can only be used to prove security results if the only mechanism that the subjects use to communicate and share data is through the operating system. But this is not the case because subjects can talk, outside of the computer system, outside of the operating system's control. So this is a reason why the star property is kind of nice to state formally, but it's very hard to enforce. So one more issue with the BLP model that I want to mention is the idea of dynamic security models. So the BLP model, as we stated, it cannot handle dynamic changes to the security level, but there have been extensions of it that have what we call tranquility properties. So the idea of tranquility, you can have a strong or weak tranquility, and that kind of measures how much the security levels or labels are changing over time. So if you have a strong tranquility, that means that pretty much the security labels do not change. And that is the basic BLP model. In a BLP model, every document, every subject is assigned a label, and that never changes. So obviously, this is impractical because in the real world, this is not the way things work. I mean, clearly, in an actual system, people get promoted. So their security clearance might go up, or people get demoted or even fired, in which case their security clearance is removed or lowered. So that means that the security labels are definitely changing through the life of the system. So strong tranquility, which assumes that the labels are not changing, It's definitely not a realistic model. And this is the same for documents and resources, obviously. Some documents get declassified, so their label changes over time. So this strong tranquility assumption is impractical. And so people have developed more general models that handle so-called weak tranquility, where labels can change over time, but they don't change too often. And when they change, they do so without violating the security requirement laid out in the policy. Now, this ends up to be very hard to do. In fact, these properties are somewhat vague and they're somewhat hard to understand. So I don't really want to go into detail uh, into these extensions of the BLP model. I just wanted you to know and get at least hear the name of the Bell-LaPadula model and know that there are people who are working on these multi-level security systems within the context of mandatory access control policies. And the way they do it is do it at a very abstract or formal level, where they establish these formal properties and if this can be proved to hold in an actual implementation of the system, then the nice feature is that we have these security guarantees that automatically follow, like in a mathematical way, from these policies. But again, remember that in practice, it is very hard to model an actual complex information system that satisfies these formal properties.